All right, today we're going to look at lesson 7.2, integration by parts. You've already reviewed 7.1, which is integration techniques, and it was all stuff in Calculus 1 you already knew how to do. But there are some things we encountered, such as the integration of natural log of x dx, that you don't know how to integrate yet. And the key to unlocking this one is integration by parts. So jumping straight to the formula for integration by parts is uv minus the integral of v du. And you have to choose a u and you have to choose a dv to be able to figure this out. So probably the best way is just to jump straight to an example. So let's look at x e to the x dx. Now, when you integrate this, you might start looking and trying to figure out, do I know how to integrate this by methods I learned in Calc 1? So you think, well, the integration of e to the x is e to the x, but that x is what's confounding the situation. So we really don't have any techniques up until now to do this. And that's where we're going to use integration of parts. Once again, remember, it's uv minus the integration of v du. So what we're trying to do every time, you're going to choose a u and you're trying to choose a dv. Now, to make the decisions here about which one you choose, you're really looking for the functions that's going to disintegrate. It's going to degenerate down to 0. So I could choose either x or e to the x for my u. And I'm going to choose x because I know eventually the derivative of that is simply dx. And the derivative of 1 would be 0. So that one's going to eventually disintegrate. So that leaves me e to the x dx for my dv. And when I integrate, so you got to take the derivative of one side and integrate the other. So the integration of that dv is the same as the integration of e to the x dx, which is simply e to the x, and that is my v. So substituting that into integration by parts, that we know that uv, so x is my u, v is now e to the x, minus the integral of v, which is e to the x, du, which is dx. So now when we integrate e to the x minus integration of e to the x is e to the x plus some c. And that is our answer. Now all of a sudden it really opens the door to all kinds of things that we can integrate. All right, let's look at another example. Actually, I'll tell you what, let's look at the integration of natural log of x dx. Since that's one that we've told you that we didn't have an integral for all through Calc 1, now you're going to learn how to do it by integration by parts. So remember, the integration by parts is uv minus integration of v du. Now I'm going to choose u to be natural log of x this time. And the reason is, if I chose that for my dv, the whole point of this is trying to integrate natural log of x, so I can't choose that for my dv. So that leaves the only thing left to put for dv is dx. Well, we know that du is the derivative of natural log of x is 1 over x, or dx over x. And we know that the integration of dx is simply x. So now my integration of parts uv is x. uv is natural log of x times x. So I'm going to write that as x natural log of x minus the integral of v du, which is v is x and du is dx over x. In other words, we're doing x natural log of x minus, the x's cancel out, the integration of dx, and finally after a year of waiting, you now have integration of dx is x. You now have a formula for the integral of natural log of x. You didn't need to memorize it because now you know how to derive it using integration by parts. All right, let's do another example. Let's look at what happens when you integrate, this time, x squared natural log of x dx. Well, remember, integration by parts, uv minus the integral of v du. And it probably is helpful to write that down with every problem so you know what you're looking for. Now, I said choose my u to be the function that disintegrates, which would be the x squared. However, once again, we don't know the integral for natural log of x, or we do now, but we don't want that messy formula in. So instead of my x squared being my u, I'm going to let my x squared be my dv. And my u is now natural log of x. So now du is dx over x, and v is equal to 1/3 x cubed, just integrating that. Putting that in my formula now, we got uv, so it's 1/3 x cubed natural log x. That's actually vu is written, but it looks better that way. Minus the integral of v, which is 1/3 x cubed, du, which is dx over x. So it's 1/3 x cubed natural log of x minus 1/3 x cubed divided by x is x squared dx, and of course we're integrating that. So it's 1/3 x cubed natural log of x minus 1/3 times the integral of x squared is 1/3 x cubed. So now we have 1/3 x cubed natural log of x minus 1/9 x cubed plus c, of course, and we've integrated. Well, you can even do this with art inverse trigonometry. So we never memorized any formulas for inverse trigonometry, but now you have the skills to figure out what the integral of arc sine is. Remember, uv minus integral of v du. So I have to choose a u. Well, I know the derivative of arc sine, so I'm going to probably choose that for my u, and that means my dv is simply going to be dx. But du equals the integral, the derivative of arc sine is simply 1 over square root of 1 minus x squared. And then my v is going to be x if I integrate that. So setting this up, we got uv, so x arc sine x minus the integral of v, which is x, du, which is 1 minus x squared square root. So what I did is v du, that is dx, by the way. So that's putting those together. Well, this is simply u substitution. So I'm going to choose another u. I'm going to say, well, what happens if I would have said let u equals 1 minus x squared. Now du is going to be negative 2x dx. So what I'm really, let me rewrite this so we can have enough room to work. X arc sine of x minus integral of x over square root of 1 minus x squared dx. So now this is simply, and you reviewed these techniques in the last section, but this is u substitution. I need a negative 2x here to have the derivative of what's inside, which means I need to bring a negative 1/2 out here. So now I have basically 1/2 plus 1/2 the integral of du over the square root of u, which is x arc sine x plus 1/2. It's the integral of u to the negative 1/2 du. X arc sine of x plus 1/2. The integral of u to the 1/2 is u to the positive 1/2. Dividing by 1/2 same as multiplying by 2. And remember, my u was 1 minus x squared. So basically, those cancels out and leaves me with the integral being x arc sine x plus the square root of 1 minus x squared. All right, I want to look at an interesting one. Well, actually, before that, I want you to think. All right, sorry about that. If you were referred to in your book to page 493, there is a chart there that gives you kind of the rules on which one to choose for u and which one to choose for dv. I'll give you these hints. Pretty much any time you have a e to the function, use that as your dv. Otherwise, you're trying to maybe choose your oscillating function, your sine and cosine, to be your dv. And if you have natural log in there, always use that for your u. And this kind of tells you when and where to do it. Interesting happens when you have both an e and a trig function, and kind of the e overrides that. So normally if we had a trig function, that'd be our dv, or normally if we had a e to the x, that'd be our dv. In this case, if you have both of them, you're going to use your e to the x to be your dv. And so let me look at an example where that happens. All right, so back to here. So this is an interesting problem because it seems like you're going to be going in circles. We have the integral of e to the x sine x dx. And I just said let's go ahead and do our e to the x always is dv. So u is sine x and dv is going to be e to the x. So du is cosine x and v is e to the x. All right, that seems pretty straightforward. So what I have is the integral of e to the x sine x is equal to uv, so e to the x sine x, minus the integral of v du, e to the x cosine x dx. Well, it looks like we have another integration by parts in here. So basically, I have the integral of e to the x sine x is equal to e to the x sine x minus, and let's do integration by parts again. So for this part here, I'm going to say let u equals, this time cosine x, du is equal to negative sine x. But dv equals e to the x, while v is equal to e to the x. So uv would be e to the x cosine x minus the integral of v, which is e to the x, du, which is negative sine x, and I'm going to put my negative out there. All right, let's see what we have. Looks like I'm going in circles. So I have the integral of e to the x sine x is equal to e to the x sine x. Put this out of the way. Okay, I'm distributing this negative through. Minus e to the x cosine x minus the integral of e to the x sine x. And that's where we started, was e to the x sine x. So I don't feel like I've really got much accomplished here. Let me see if I can get myself some more room to work with here. All right. Now there's a reason why, in the other ones I didn't keep writing down the problem, and I wrote it down this time. I want you to see this little trick. Watch what happens if I add the integral of e to the x sine x to both sides. By the way, this is dx, I'm not writing this. So if I add that to this side, it's kind of a neat little trick. What I end up with is I have two of the integrals of e to the x sine x, and that's equal to e to the x sine x minus e to the x cosine x. And my whole point was to figure out what e to the x sine x is, but now if I divide both sides by 2, those are gone, and I figured out what the integral of e to the x sine x is. It's e to the x sine x minus e to the x cosine x divided by 2. I'll be around shortly, and if you have questions on that problem in particular, I can definitely answer. All right, that's integration by parts, and that should work. You'll be able to integrate a lot more than you've been able to integrate before. There is a kind of a shortcut to integration by parts called the tabular method, and you can see that on the bottom of page 493 in your book. If the tabular method doesn't help you, I don't even want to put it in your brain, but for those of you that like little shortcuts, here's a shortcut to it. So you may go ahead and work on the homework and come back to this part of the video, or if you want to follow me through the tabular method, there is a way to do that. What happens sometimes is you have to keep doing integration by parts. By the way, this is the tabular method we're going to see here. All right, so you have to do integration by parts several times within a problem. And we just saw an example where we at least had to do it 2 times before we discovered our trick. But the tabular method is a little shortcut. And so if I was going to do this, I would choose u to be x squared, d would be 2x, sine of 4x would be my dv, and then the cosine, 1/4 cosine of 4x would be my, or negative 1/4 cosine of 4x would be my v. The tabular method recognizes that these things are going back and forth and that you're having to keep doing it until you get the x squared down to 0. So the tabular method is choose the u like you normally would. So in this case, x squared. Choose your dv, in this case, sine of 4x. And I'm just going to go ahead and, since I know I've got to keep taking the derivative of that, I'm going to take the derivative of x squared until I'm down to 0. So 2x, 2, and 0. Now this side over here on the right, I'm going to have to keep integrating sine of 4x. So the integration of sine of 4x is negative 1/4 cosine of 4x. And the integration of negative 1/4 cosine of x is negative 1/16 sine of 4x. And the integration of that is a positive 1/64 cosine of 4x. The tabular method says that you can take, whenever you start with u, and draw the arrow down to your second step of your dv. You take your arrow down and your arrow down until you run to the 0 and then you do nothing. Another important part of the tabular method is the alternating signs. So this one's positive, negative, positive, and since that's 0, it doesn't come up there. But you alternate until you get down to your 0. So what you're going to do every time is take this one, the top, times the one it leads to. So this integration, by integration by parts, but taking a shortcut with the tabular method, is negative 1/4 x squared cosine 4x. So basically I just took that one times that one. Now that minus right here is going to be used now. Minus, but this is positive times a negative. Positive times a negative, so that's going to be a positive. 2x over 16, or 2x times, I'll just write it out without simplifying, 1/16 sine of 4x. All right, now I'm ready to take care of the other one, which is now a positive, so plus 2 times 1/64 cosine 4x. So I took 2 times that one. And now that I'm to the 0, I'm done. So this really has 3 components to it. I'm going to just rewrite it again so it looks a little bit neater. So this one here is equal to, looks like we have negative 1/4 x squared cosine 4x. Plus, simplifying this a little bit, 2/16 would be 1/8 x sine of 4x. Plus, and 2 1/64 is 1/32 cosine of 4x plus c. And that is the answer. And you could have done that traditionally with integration by parts and just had to do integration by parts within integration by parts. The tabular method is a little shortcut. Some students like it, some don't. You decide if you want to use it or not. All right, thank you. I'll be back if anybody has any questions.